Hello everyone, welcome to this video lecture of 19ScPhyU301. We have been discussing the third chapter, vector analysis, and this is the story so far. We defined the del operator, which is a vector first order differential operator. Then we also defined Laplacian operator, which is written as del square, which is obtained by taking dot product of del operator with itself. This Laplacian operator is second order scalar differential operator. When we operate this del operator onto some scalar field phi, then that is called as gradient of that scalar field, and that gives us rate with which the scalar quantity changes per unit length with maximum amount. So it is a vector quantity, and the direction is also in the direction in which the phi changes with maximum rate. Then we also saw that when we take dot product of gradient of a vector with a unit vector, then this quantity is called as directional derivatives, and this gives us rate per unit length of change of scalar phi along the direction given by this unit vector u. When we operate this del operator onto a vector field, then that is called as divergence of the vector field, and divergence gives us net flux per unit volume outside infinitesimal small volume about the point where the divergence is calculated. When we consider divergence, we also saw the divergence theorem, which is a way to convert volume integration to surface integration. Mathematically, Gauss's divergence theorem is written like this. It is del dot V over volume d tau is equal to V dot ds. Note here that this left hand side is volume integration and therefore is a triple integration, whereas the right hand side is surface integration and therefore is double integration. In the previous lecture, we considered curl of a vector. When we can calculate this, when we perform this operation, then it is called as curl, and it gives us line integration per unit area enclosed by a closed loop. When we considered the curl, we also saw the Stokes theorem, which is a way to convert surface integration to line integration. Mathematically, it is written like this. It is del cross V ds is equal to V dot dl, and this is a line integration over a closed loop, which is denoted by this circle here. In this lecture, we want to discuss Maxwell's equations. These four laws together are called as Maxwell's equations, which already existed when Maxwell proposed his electromagnetic theory. Maxwell did add one term in Ampere's circuital law, which is called as the displacement current. We will see it. These four equations together are called as Maxwell's equation because by using these four equations and the displacement current that Maxwell himself added to Ampere's circuital law, Maxwell showed that light is electromagnetic waves. These equations together can give rise to wave equation. What we will do in this lecture is we will consider each of these laws and we will see the integral form of this law which is commonly associated with these laws, and we will then see the differential form of each of these laws. So let's start with Gauss's law of electricity. When I write Gauss's law, it is for the electric field. What is it? Can someone tell me what is Gauss's law? Flux through closed surfaces Q by epsilon, where Q is charge enclosed by that closed surface and the flux we are talking about is flux of electricity. So Gauss's law states, first law states that flux of electric field over a closed surface is equal to charge enclosed by that surface. What it means, suppose I have this closed surface, it could be of any shape, and if I calculate this flux of electric field through this closed surface, that means it is this surface integration that we have seen, E dot dA, we have written, let's use the term ds. So E dot ds this flux of electric field through this closed surface or outside this closed surface is equal to Q enclosed. So net charge which is enclosed by that surface, irrespective of what is the position of that charge, as long as that charge is enclosed by this closed surface, then this is the equation for Gauss's law. This EDS over a closed surface is equal to Q enclosed divided by epsilon 0, right? So now let's try to rearrange this equation a bit. As I said, this is the integral form. This is the first Maxwell's equation. Gauss's law is the first Maxwell's equation, and this is integral form of this first Maxwell's equation. Now what we will do is we will rearrange this equation a bit. Let me keep for now left hand side as it is. EDS is equal to 1 by epsilon into, I'll write this as rho, which is a function of R in general, into d tau, where what is d tau? It is volume element, right? And what is rho? Rho is charge density at the given point, right? And therefore when you consider this integration, it gives you the net charge, because that is how charge density is defined. So this is how we can rearrange this equation, the right hand side of the equation. Now let me use Gauss's divergence theorem. What is Gauss's divergence theorem? What does it do? By using Gauss's divergence theorem, you can convert surface integrals to volume integrals, and therefore this EDS, which is a surface integral, can be written as del dot E integrated over the volume, right? And let me use this right hand side on the left hand side of this equation, and what we get is this. So what we get for the Gauss's law is del dot E d tau is equal to 1 by epsilon rho, which is function of space, it is rho of R into d tau. Okay, and now these are, you can see that there is integration, both of them are integrals over the volume, and therefore I don't have to consider this integration. I get the differential form, which is del dot E is equal to rho by epsilon 0. So this is Gauss's law, and it is the differential form. Which happens to be the Maxwell's first equation. Okay, Gauss's divergence theorem in this mathematical statement, in this formula of integral form, and you get the differential form, right? Is this clear? Any questions in this? Shall we move on then? Let's consider the Gauss's law for magnetic field, right? And the statement is clear here that magnetic monopoles does not exist. What does that mean? It simply means that if we consider flux of magnetic field over a closed surface, just like we consider it for electric field in the first law, in Gauss's first law for electricity, then it should be equal to net magnetic poles which it considers. But we know that if you have north pole, there is definitely south pole associated with it. You cannot break this magnet and obtain only north pole, because if you do it, if you cut the magnet into two pieces, what you get is again north and south poles. So magnetic monopoles, therefore they don't exist, and therefore whenever we consider this closed integral, suppose I have this closed surface, and if I consider this flux of the magnetic field outside this closed surface, then this is always equal to 0. Why? Because magnetic monopoles does not exist. Magnetic field is always present as in terms of two poles. There are always two poles present, and therefore this is the equation that we get. Now again I can use, what is this form? This is integral form. So this is second Maxwell's equation. Okay, and this is the integral form of that second equation. Now I can use divergence theorem here and write the left hand side, which is a surface integral b dot ds, as volume integration, which is del dot b over some volume d tau. And therefore this equation, this integral form of second Maxwell's equation, can be written as integration del dot b d tau is equal to 0. And since we have 0 on right hand side, we can write the differential equation right away, differential form of that equation right away, which is del dot b is equal to 0. Is this fine? So what is the first, which is Maxwell's first equation? It is basically the mathematical statement of Gauss's law for electricity. Then Maxwell's second equation is mathematical statement for Gauss's law for magnetic field, which basically is equal to 0 because magnetic monopoles do not exist. This should have been, yeah, it's fine. So therefore this is the integral form of second Maxwell's second equation, and this is the differential form of that. Is this fine? Any questions in this equation so far, in second equation? Okay, which is the third equation now, or which is the third law which gives the third Maxwell's equation of electrodynamics? It is Faraday's law of induction, right? So what is Faraday's law of induction? It is this mathematical statement is this. Now what is phi b here? Phi b is magnetic flux. So it is calculated like this. If b is magnetic field vector, then phi b is b dot ds. Whatever is, suppose I have this surface and magnetic field is in some direction, something like this. Then when we calculate this phi b, what we do is we divide this area. It is now not closed area. Remember, it is this area which is open. We divide this into infinitesimally smaller area segment. At each of the area segment, we calculate the dot product of b and ds vector, where ds vector is a vector with magnitude same as area of that area element into unit vector which is normal to that area element. So in this way ds is defined at every of this area element. Now you take the dot product and you go on adding all these infinitely many and infinitesimally small area dot product for all these area elements, and that way you calculate this phi b, which is called as magnetic flux. And then Faraday's law of induction says that EMF is induced whenever there is change in flux, magnetic flux. What is direction or what kind of electric field is induced? Let me continue on next slide. So this epsilon is nothing but a voltage. It can be written like this, E dot dl, where if magnetic field is changing in this direction like this, then this EMF induced is in this direction. This negative sign makes sure that it is in the opposite direction in which the magnetic field is changing, right? This is a vector field. And this E is now not the electrostatic field. It is electric field, but it is electrodynamic field which is produced due to changing magnetic field. And the difference between electrostatic field that we consider for Gauss's law and this electric field is that this electric field which is induced here is non-conservative. And therefore, if you consider electrostatic electric field or static electric field, and if you consider curl of that electric field, it is always equal to 0, because static electric field is a conservative field. But when it comes to this Faraday's law of induction, when it comes to this EMF induced and electric field which is associated with that electric field is now non-conservative electric field, and therefore del cross E is non-zero. It is no longer 0. What is third Maxwell's equation? It is this integration EdL over a closed loop now, because if magnetic field is changing in this direction, then this gives rise to a closed loop in which the electric field is induced. In fact, that is the reason that the curl is not 0. The line integration of this electric field over the closed loop is not equal to 0, but it is equal to minus dou phi b by dou t, where phi b is the magnetic flux, which can be calculated by considering this integration b dot ds. So it is surface integration over the closed loop. Now what we will do is we will use Stokes theorem here. What does Stokes theorem do? It converts line integration to surface integration. Therefore, this EdL over the closed loop is equal to del cross E integrated over the surface. And this ds basically means the surface which is enclosed by this closed loop. This is the same ds over which we are integrating the magnetic field to calculate the magnetic flux. And therefore, this equation can be written as del cross E integrated over the surface is equal to minus integration dou by dou t. Since we are differentiating it with respect to time, and here you don't see any explicit time dependence, I can either write this differentiation outside the integral sign or inside it. It won't make any difference. And therefore, this is now dou t of b ds. Okay. So you can see that this integration is over the same area. It is the same surface integration, and therefore I can write this equation now even without the integration sign. And if this is the integral form of Maxwell's third equation, then its differential form is obtained when we write this equation without the integration symbol, which is equal to, let me write it here, del cross E is equal to dou B by dou T. Rate with magnetic field is changing when it is written explicitly as a function of time. Okay, just see what has happened is this phi b has now become only magnetic field, because we are not considering the integration over the surface now, and that is the same thing we are doing on left hand side. And therefore, in this way we obtain Maxwell's third equation in its differential form. Oh yeah, thank you. So shall we move on then to the next equation, Maxwell's fourth equation? Any other question? What is it? Yeah, I kept one slide. Ampere's circuital law basically gives, suppose uh, there is a wire which is carrying some current in this direction, and if you now consider this loop which is enclosing that wire which is carrying current I, then Ampere's circuital law that you saw in last semester is this: line integration of magnetic field over this closed loop. Since it is a closed loop, I have to denote it by a circle, which is equal to mu 0, or rather mu, into I enclosed, where mu is permittivity of the medium in which we are considering this particular current. Let's now stick to vacuum. So if if everything is in vacuum apart from that current, we have mu 0, which is permittivity of free space, and that is basically this equation for Ampere's circuital law, right? So you understand that this is not the full story. This is only half of the story, because there is one more term which was added by Maxwell. So this is the contribution, his own contribution to these four equations. So he added this term in Ampere's circuital law. And what is that term? Suppose I'll briefly explain that. I'll try to explain that. Suppose you have this parallel plate capacitor. Okay, this is a battery with some voltage V. And now what you do is, there is this key initially, this capacitor is not charged. So there is no charge on the capacitor. Now, when you just close this key, what will happen? Or after, suppose you close the key and you look at the whole circuit after a long time, what will happen? You will see that this capacitor is charged. This plate has positive charge accumulated on it. This plate has negative charge accumulated on it. And now, since these are charge separation, there is a voltage difference between these two plates, which is equal to V, and it is in the opposite direction of that of battery, and therefore this is a steady state where no charge flows in the circuit. But this is the situation which is called as steady state because this happens after a long time after you close the key. So when if initially when this key is not closed and you just close this key, what happens is current starts flowing. Current will flow in this direction, so that this plate will start accumulating positive charge and this plate will start accumulating negative charge, and this charges q now are function of time. This small current will flow initially. This current is called as the current which flows in the circuit for a very short time before this capacitor is fully charged and have voltage equal to V, which is voltage of the battery. This current is called as transient current. So this transient current flows through the circuit, and when the current flows, this Q, which is charge accumulated on any of this plate, is a function of time. Okay, now let me consider this charge capacitor. Okay, I'll draw that here. And suppose this charge is now building up. Now let me consider this surface, which is closed surface. So I'm considering this as a cuboid, though you can see only the rectangle. What I'm trying to draw is cuboid. So there are these how many 6 surfaces there to this closed surface. And now what we will do is this Q, which is charge on this capacitor, positive charge on the capacitor, we will use Gauss's law for this particular case, Gauss's law of electric field. So what we know is E dot ds over this closed surface, which encloses this positive plate, is equal to Q enclosed, which is a function of time now, divided by epsilon 0. If we consider that this is a free space, if there is no dielectric medium field in the two plates, then this is epsilon. It is permittivity of free space now. If there was some dielectric field in there, then this would become epsilon, which is permittivity of that medium. For now, we can write it as epsilon 0. Okay, for free space. Now, if you calculate this this surface integration, you have to consider all 6 surfaces. This surface, which is the top surface, it is in 3D now. It is inside that screen. This is the bottom surface. Then you have a surface which is parallel to the screen, which you can say is the front surface. You have to imagine that now. I am not drawing it there. And then there is back surface, which is also parallel to the screen, and it is inside the screen, so that we have a closed surface there. Now, if you consider these 6 surfaces, 1, which is top surface, 2, which is bottom surface, 3, which is this front surface, 4, which is the back surface, which in this 2-dimensional diagram is overlapping on the front surface, and 5, which is the surface outside that charge capacitor. For all these 5 surfaces, or except this surface now, the electric field is in this direction. So it is perpendicular to surface vector. It is perpendicular to normal vector for each of these 5 surfaces at every point. Ether electric field is in this direction, whereas the surface is pointing upward. For bottom surface, the vector or normal to the surface is pointing downward, and electric field is perpendicular to that, and therefore this dot product is 0. For the front surface, the direction of the surface is perpendicular to the screen coming towards you, and again it is perpendicular to the electric field, and the dot product is 0. And for the back surface, again the direction of the normal to that surface is inside the screen, perpendicular to the screen, and again it is perpendicular to electric field. So for these 5 or 4 surfaces, this E dot ds is equal to 0. For this fifth surface, for a parallel plate capacitor, electric field outside it, outside the charge capacitor, is always equal to 0, and therefore E is 0 for that fifth surface, and therefore this surface integration over the closed surface has 6 parts of the surface to it. Out of these 6 surfaces, only one surface, which is this surface, which is perpendicular to the screen going inside it, is in the same direction as the electric field, and that is the only surface which will contribute to the dot product, and therefore this integration over closed surface now can be written as E dot ds. So this circle is now gone, because it is no longer integration over the closed surface, it is integration over only this surface which is perpendicular to the screen going inside, such that at every point normal to the surface in the same direction as the electric field, and this is normal to the surface, and therefore this is only the dot product which contributes in non-zero terms for this closed interval, and therefore we get integration over the surface, which is now not a closed surface. And this left hand side, let me keep it as it is. Now let me differentiate it and get dou E by dou T dotted with this surface integration is equal to 1 by epsilon 0. This is dq by dt. Now remember, this q now is not current. There is no current, actual current in the sense as it flows in the wire. It is just the current which is there because the electric field is changing. So in this region, since this charge q is building, electric field is increasing, and this dq by dt have the same dimensions of that of current, but it is not actual current which is produced due to flowing charges, but it is produced due to increasing electric field. Again, remember, when I differentiated it with respect to time, I forgot to mention that, so when you differentiate this equation with respect to time, this ds is independent of time, and therefore I don't have to use u into v rule. Only E can be function of time, and therefore we get this relation. So I was saying this dq by dt now is not actual current. It is, or rather it is not produced due to flow of charges. It is produced due to increasing electric field. And this current is called as the displacement current. Sometimes it is written like, let me write it like this. And this is the second part, or this is the complete story for Ampere's circuital law. So Ampere's circuital law therefore now is integration B dl over closed loop is equal to mu 0 I, which is due to free charges. So this there could be actual free charges which are moving, giving rise to current, and therefore we have this current plus, and then I have this current. Yes, I have to rearrange that equation. Nothing is wrong. So if I rearrange this equation, what I get is, let me do it here itself. So what I get is epsilon 0 into dou E by dou T integration ds is equal to dq by dt, where this dq by dt now is the displacement current. So when I write Ampere's circuital law, I have to consider both the current. One is the current due to free charges, and the second current is due to this displacement current due to increasing electric field as a function of time, and therefore the second term is mu 0 into dou E by dou T dot ds, and it is integration over the surface. So this was only half of the story. The second part of displacement current was introduced by Maxwell, and the story then is complete, which is, this is the second part. This is the displacement current second part of the story of the Ampere circuital law, and this is the complete equation, right? Yes. What can you see the change here? See, when I wrote that displacement current, it is epsilon 0 integration dou E by dou T into ds. Now what you can do is, since you can take this differentiation outside integration side, what you get is E dot ds, and this is now nothing but the electric flux. Therefore this is dou phi E by dou T, where phi E is dou E, sorry, it is phi E is the flux of electric field. Now we have to rearrange this equation. So the Ampere circuital law now is B dot dl is equal to mu 0 into I enclosed, which I can write it as J ds, where J is the current density, plus the second part of displacement current is mu 0 epsilon 0 into integration dou E by dou T dot product with ds, where J is current density. And by definition, if J is current density, then I is obtained by this surface integration. I can use Stokes' law and write this integration of magnetic field over closed loop as del cross B over ds, integration del cross B integrated over the surface, which is equal to mu 0 J ds plus mu 0 epsilon 0 integration dou E by dou T ds. Now since all of them are integrated over the surface, we can write this equation as del cross B is equal to mu 0 J, which where J is the displacement current, J is the current density, plus mu 0 C is equal to 1 by mu 0 epsilon 0. Speed of light in vacuum is given by this relation, and therefore mu 0 epsilon 0 is nothing but 1 by C square into this dou E by dou T. Okay, I'll write it here. So Ampere circuital law, when you write it in differential form, you can write it as del cross B is equal to mu 0 J plus 1 by C square dou E by dou T. So this now is Ampere circuital law with contribution by Maxwell for this displacement current. So this is the displacement current term. Now that is not actually displacement current, it is displacement current density. And this is the differential form of Ampere circuital law, which is the fourth Maxwell's equation. Okay, so let's summarize and write all the laws, all the Maxwell's equation in integral and differential form. So the first equation is Gauss's law for electricity. Its integral form is this: E dot ds over closed surface is equal to Q enclosed divided by epsilon 0. Its differential form happens to be del dot E is equal to rho by epsilon 0, where rho is charge density at any given point. This is now the differential form. So we have to consider this dot product or this divergence of electric field at any given point, and this rho is charge density at the point where we are calculating the divergence of electric field. Then we consider Gauss's law for magnetic field. I'll simply write magnetic monopoles do not exist. Magnetic, or I'll write absence of magnetic field. Absence of magnetic monopoles which for which the integral form is b dot ds is equal to 0 and its differential form is del dot b is equal to 0. The third law that we considered was Faraday's law of induction. Let's write it in integral form. EdL over a closed loop is equal to minus dou phi b. Okay, let's write this also in integral form. Dou t of b ds, where remember b ds is flux, magnetic flux, and its differential form now is del cross E is equal to minus dou b by dou t. Then fourth law is Ampere's circuital law, and Ampere's law with the correction with the displacement current, and therefore what we have is, what is it? It is now BDL over the closed loop is equal to, I'm sorry for extending the lecture, but let's finish it. This is equal to mu 0 JDS plus 1 by C square dou E by dou T dot ds. So this is electric flux now, and its differential form, which is the fourth Maxwell's equation, is del cross B is equal to mu 0 J plus 1 by C square dou E by dou T. Right? So we have written all four Maxwell's equations in integral form and in this differential form. We have come at the end of this lecture, and this is the last lecture on this chapter of vector analysis. From next lecture, which is on Saturday now, we will begin with the fourth chapter, which is Fourier series. Thank you for watching.